Welcome to The Explainer. Today, we're cracking open Andrei Burkhoff's The 100-Page Machine Learning book to get right to the heart of how machines really learn.
So, let's kick things off with a fact that might surprise you. That term we hear everywhere, machine learning. It didn't just bubble up in a research lab. It actually got its start as a pretty brilliant marketing gimmick.
Yeah, check this out. It goes all the way back to 1959. A guy named Arthur Samuel, a real pioneer at IBM, coined the phrase. And IBM, being savvy, quickly realized, hey, this sounds really futuristic and cool. So by the 60s, they were using it to make their work stand out, to grab the best engineers and land new clients.
And this quote from Burkhoff himself really hits the nail on the head when it comes to the difference between us and them. What he's saying here is that these systems can be incredibly brittle. Think about it. You can see a weirdly drawn picture of a dog and you still know it's a dog. But for a machine, if you change the input just a little bit, it can get completely confused. It doesn't truly understand, it just recognizes patterns it's seen before. Powerful? Yeah, but also fragile.
Okay, so if it's not learning like we do, then what is it doing? How does a machine learn? Well, it really boils down to two main playbooks. First up, you've got supervised learning. The analogy here is perfect. It's like giving the machine a study guide with the answers in the back. It learns from a whole bunch of data that humans have already labeled correctly. Then there's unsupervised learning. This is where it gets really interesting. Here, there's no answer key. The machine is more like a detective thrown into a room full of clues, and it has to figure out the patterns and connections all by itself.
All right, let's bring this down to earth with something we all deal with, probably more than we'd like to. The good old spam filter in your email. This is a classic, perfect example of supervised learning in action.
Have you ever stopped to wonder how your inbox actually knows that an email is junk? It's not some kind of digital wizardry, I promise. It's a surprisingly logical, step-by-step process. It's basically a four-step dance. First, you've got to gather your data. And I mean a ton of it. Thousands and thousands of emails that a real person has already marked as either spam or not spam. But here's the catch. Computers don't read English. So step 2 is the really clever part. You have to turn all those words into numbers. We call this creating feature vectors. Once you've got numbers, then you can finally train your model with an algorithm. And the last step, you set it loose. It starts predicting, in real time, what to do with every new email that hits your inbox.
So how in the world do you turn an email into a string of numbers? Well, a really common way is called the bag of words method. It sounds kind of funny, but it's simple. You just create a big checklist of words. For every single email, the computer just goes down the list. Does it have the word Viagra? Yep, that's the one. Does it have bye? Yep, another one. Does it have my colleague's name, Aaron? Nope, that's a 0. All of a sudden, that messy email becomes a clean, simple code. An email full of spammy words is going to have a totally different numerical fingerprint than a normal one, right? And that's how the machine starts to see the difference.
Okay, so now you've got all these emails represented as points, as numbers. You can imagine plotting them on a giant graph. Of course, since there are lots of words, this isn't a simple 2D graph. It's a huge, high-dimensional space. And the whole point of the learning algorithm is to draw a line, or more accurately, a hyperplane, right through the middle of that space. Everything on one side of the line is spam, and everything on the other is not spam. That line is the key. It's the decision boundary.
And this idea, it's not just for spam filters. It's huge. Like Burkhoff says, pretty much any algorithm that has to classify something, we're talking spam, medical images, customer reviews, you name it, is at its core trying to figure out where to draw that decision boundary.
But here's where it gets really tricky. It's one thing to draw a line that separates the data you already have. It's a whole other challenge to draw a line that will work for new emails it's never seen before. And that brings us to maybe the single biggest headache in all of machine learning. Something called overfitting. Overfitting is exactly what it sounds like. The model fits the training data too well. It doesn't just learn the general rule, it memorizes every single detail, every little quirk and bit of noise in the data it was trained on.
The student analogy is perfect. It's the student who gets 100 on the practice test because they memorize the answers, but then completely bombs the final exam because the questions are different. They didn't learn the concept, they just memorized the examples.
So you end up with this classic Goldilocks problem. You can draw a line that's way too simple and it misses the pattern. That's underfitting. Or you can draw a crazy, squiggly line that hits every single data point perfectly. That's overfitting. What you're looking for is the line that's just right, the good fit, the one that captures the real trend without getting obsessed with the noise. That's the model that will actually work out in the real world.
Which leads us to this legendary quote from the statistician George Box. It's practically the mantra of machine learning. All models are wrong, but some are useful. Think about that. The goal isn't to be perfectly right, because a perfect model is probably an overfitted, useless one. The goal is to be useful.
So, let's just recap what we've covered. Machine learning isn't magic, right? It's a process. It's about finding useful patterns. We saw how supervised learning uses that labeled data, our answer key, to draw these all-important decision boundaries. But we also saw that the biggest trap is overfitting, which is why we're not chasing perfection. The whole game is about building a model that's simply useful.
And that leaves us with a really big, important question to chew on. If the goal is just useful, not perfect, then in a world that's being shaped more and more by these models, how do we know which ones we can actually trust? And who gets to decide? That's not just a technical question anymore, it's a question for all of us.